Hi everybody, today you're going to learn about evaluating functions. This is actually a skill you've been doing all year. The only difference is today you're going to do it with the function notation, which is really just a fancy kind of way to talk about using inputs and getting only one output. All right, so at this time I'm going to have you go ahead and pause your video and complete the 4 warm-up questions. When you're done, go ahead and unpause the video and we'll see how you did. Okay, so when we look at domain, we are dealing with the x values. And I've tried to highlight here what we're dealing with. So domain is from left to right. So if you go from the left to the right, I've highlighted where the graph exists. It starts at -2. And finishes over here at +2. And since it's a continuous curve, we're going to say that -2 is the left endpoint, and that the x values, so we'll say -2 is less than or equal to x, and then that has to be less than or equal to +2. All right, so we're basically giving the left endpoint on the end here, the right endpoint over here, and the arrows all point towards the smaller numbers. If you wrote it the other way, that's totally fine too. You just have to realize that you'd have to switch your arrows to point to the smaller number. You're always eating the larger number. Range, we can play the same type of game here. We're going to start at, again, low to high. So it starts at 0. Finishes at 3. So we'll say 0 is less than or equal to y, which is less than or equal to 3. So that just means the y values are all between 0 and 3. All right. Is it a function? Well, if you draw a vertical line through the graph, that's a little wide. If you draw a vertical line through the graph, you can see that as I slide this through the image, like right here, it crosses the graph twice. And so, no, this is not a function. And the reason being it doesn't pass the vertical line test. And the vertical line test is just a quick way to check to make sure that, if you have a graph, to see if it is a function or not. That graph cannot cross through a vertical line twice if you're going to call it a function. So how do we write functions? Well, functions are going to be set up with this notation where they generally pick a letter to name the function. F, G, and H are really common names. They're not the only names for functions. You can really use a lowercase letter, a capital letter, uppercase letter. As long as you have designated it with some name, you can use that as your function. So this f of 6 business right here, this is something that a lot of students will misread and misunderstand. They will think that this notation means that you are taking a variable f and multiplying it by 6. And that is not the case. Function notation is set up. Oops, sorry about that. Function notation is set up so that it shows an input of 6 is being plugged into the f function. All right, and this will make more sense once we do an example. So your input goes into the function, and then you spit out an output, but there's only one output for every input that we put into the function machine. So we'll do a couple examples here just to give you a taste of what these are going to look like. When you come to class tomorrow, we'll be making some posters where you get to practice this in class, and we'll give you a little bit more feedback on it. Okay, so this is the function. This is the actual side of the function where we're going to do our calculation. And the left side just tells us the name of the function is h. The name of the function is h, and the x just says that's our input. So our input is x. Which x are we plugging in? Well, if you look right here, it says we're going to input 8 into the function. So h of 8 doesn't mean we're multiplying 8 times h. That just means on the right-hand side, every time I see an x, we are going to replace it with the number they gave me. So we're going to take x here, and we're going to replace it with 8. And we're just going to evaluate this right side by multiplying 5 times 8 and subtracting 6. So h of 8 would give us 40 minus 6, which is 34. All right, and maybe another way to think about that is that if you have an input of 8, we have an output of 34. All right, now, you don't have to write this ordered pair out, but I just wanted you to show you that when you see this notation, this is a fancy way of saying we used 8 as our input, we got 34 as the output. If we were to graph this function, this would actually be an ordered pair right on the graph. There'd be lots of ordered pairs that make up the graph, but this would be one particular point that falls directly on whatever it is we were graphing. So I'll show you that in GeoGebra here. All right, so the function was called h of x. I'm going to type that in my input bar. And the function was equal to 5x minus 6. And our input of 8 has an output of 34. Let's just check to see if that's accurate. Input of 8 has an output of 34. Yep, that seems very logical. Here's 8, and if you track that over, there's an output there of 34. All right. Let's try another one. So f of 18 is the next one we're going to evaluate. So f of 18 means every time I see an x on the right side of the equation, we're going to replace it with 18. So 5/6 times 18, and then we'll add 2 to that total. All right, I'm a big fan of reducing first. It makes your life easier. Maybe think of this as 18 over 1. Notice that 6 and 18 can reduce to 1 and 3. We're left with 5 times 3 in the numerator, which is 15, divided by 1 times 1, which is 1. 15 over 1 is 15. Plus 2 gives us 17. So that means f of 18, in other words, an input of 18 into this function, gives me an output of 17. And again, if we were to graph that, when x is 18, that means our y value would be 17. All right, on your last one, we have a little bit more complicated function. So we'll just evaluate one piece at a time. So h of negative 3 means we're going to take every x and replace it with negative 3. So we're going to do negative 3, and we'll take the absolute value of that, plus 4, and then minus 6 times negative 3 squared. All right, the hardest thing about this problem is just being careful on PEMDAS. So the negative 3 quantity squared, this is an exponent, so we got to do this part here first. So this part here gives me 9. And then we're going to multiply that by negative 6. Okay, and then kind of working PEMDAS, we're going to simplify this grouping symbol next. We technically could have done that first. Actually, that could have gone ahead of exponents, but in this case, it won't matter. So the absolute value of negative 3 is a positive 3. Absolute value always makes it positive. And we still have a positive 4. So h of negative 3 is going to be 7. And then this is negative 54. So 7 minus 54, which would be a negative 47. So an input of negative 3 yields an output of negative 47.